Thank you for joining us again. Welcome everyone to our webinar for structural health monitoring solutions for long-term dynamic bridge protection, brought to you by Kistler. Let me first start by introducing our speakers for today. My name is Angelica Amancio. I'm your Business Developer Manager for the West Coast with Traffic and Infrastructure Division at Kistler. My colleague, Kyle Classing, is the Business Developer Manager for the East Coast with Traffic and Infrastructure Division here at Kistler as well. And then we have Dr. Giacomo Imposa, Structural Engineer, PhD, who is a business development for structural health monitoring with us here in the Traffic and Infrastructure Division. Today's presentation, we will go through what structural health monitoring is, or SHM. And then we will take a deeper dive to what the problem is. And then we will wrap up our presentation with the Kistler offering to a solution and question and answers towards the end. Some of you may already be familiar with the Kistler name and may know us just in one facet of our technology or industry, but we are involved with several different industries in different markets. We have install base throughout the country and worldwide. Kistler has been around for over 60 years, and we have presence in any of these markets that we serve. So let's get into it. What is structural health monitoring? Structural health monitoring in bridges specifically that we will cover today involves the use of real-time sensors to continuously measure how the bridge is performing. We're able to capture data which will allow us to make real informed decisions on the structural health of the bridge. Today, like I mentioned, we will focus our application on bridges. In the US, we have extensive number of different types of bridges: arc bridges, pre-stretched bridges, steel truss bridges, cable stayed bridges, and all of these present singular problems, but very common issues throughout the industry in trying to protect and prevent deterioration of the structure itself. So today we will go over what the problem imposes, how Kistler proposes to solve this problem, and how we can support you in this. To dive in a little bit deeper into what the issue is and the problem with these structures, I will hand it over to Kyle that will dive into the problem a little bit further.
Thanks, Angelica. So just to touch on what is the specific problem that we're trying to address. As you can see on this slide, growing traffic can lead to road safety and infrastructure concerns. For example, overweight trucks have longer stopping distances and are more likely to have tire blowouts, which can be very dangerous, as I'm sure we've all seen on the road. Freight movement also continues to increase each year, while the condition of our infrastructure continues to worsen. As you can see on the lower right, more than half of all U.S. bridges are in fair to poor condition, an issue that's amplified by overweight vehicles. Now let's take a closer look at bridges in particular on the next slide. Here's a few challenges cited by ASCE in the recent 2025 infrastructure report card. For example, about 40% of all U.S. bridges were built prior to 1970, and more than half are beyond their original design life. State DOTs are challenged with maintaining older bridges, which can tend to be in poor condition and require more funding to repair. Closing bridges for major repair is also a challenge. For example, bridges with heavy traffic, essential freight corridors, or weather evacuation routes. This creates a need to more closely monitor both the traffic loads and bridge conditions in efforts to prolong their useful service life. Now let's turn to inspection challenges on the next slide. FHWA requires bridge inspections every 2 years and updated load ratings resulting from a change in either bridge condition or the design load. Visual inspections are most common, which can be dangerous, have access challenges, and typically aren't frequent enough to catch all issues. This can lead to sudden damage, in our experience, in many cases, just days after passing a routine visual inspection. Typically, repetitive and time-consuming tasks can greatly benefit from technology and automation. Now that we have a better sense of the issues we're trying to address, I'll turn it to my colleague Giacomo, and we'll talk more about Kistler's solution. Giacomo?
Yeah, thanks, Kai. Actually, I would say that you outlined very well which is the problem. And in Kistler, as maybe some of you are aware, we are expert in measurement. So I will try to explain and to show how our solution looks like. Starting from this slide, it could be really dense of information, so I would like to make it more simple and start to describe from the left. Basically, we have a different type of sensor, and for each sensor, we are able to detect any type of parameters that are really interesting for the bridges. Those inputs are basically described in the right side of the slides, so we are able to define the gravity force, wind force, and every type of action that affect on the bridge. After we have the environmental effect that is really important as temperature, humidity, rainfall. And about the structural response, in Kistler we are expert in acceleration, so we cannot for sure miss this point, but also we integrate a different type of sensor to record also strain, displacement, inclination. Obviously, the bridge stands for a limited period of time, but is affected also by the degradation phenomena as corrosion, cracks, and so on. So all this information are perfectly recorded, measured, and sent to our KIDAC that is able to convert this information from analog to digital and send all the robust dataset to our platform. Is a cloud-based where it's possible to perform analytics and after sent to the cloud, to the bridge user. You can go forward. But to explain how our solution is based, basically I try to define in this short timing our 4 main pillars. So basically we have flexibility, synchronization, sensitivity, and integration. Starting from flexibility, you can go forward. We have basically all our sensors are in our pocket. Why? Because even if there are different, as I explained you, different type of measurements, different type of sensor, with our KIDAC, so our data logger, we are able to collect any type of input, and is also really portable, compact, and we can place in different location on the bridge. And from among the specific requirements, it has the galvanic isolation, the analog to digital conversion from the most important value that is about 24-bit resolution, and heat car connection. So this important tool is able to define the flexibility of the system. Regarding the architecture flexibility, because we need to address our solution to a really complex project as bridge, our architecture basically is cluster-based. As you can see here, to keep the measuring chain as much homogeneous and perfectly robust in terms of transmission of the data, we define this type of architecture where every cluster has a limited number of transducers located in the strategically placed points on the bridge. After they are connected to the KIDAC, and for any KIDAC, in each cabinet, in each cluster, we have a switch. And after all this data are sent to a master cabinet where is located the industrial PC which process the data and send to the cloud. Another important feature is for sure synchronization, because imagine that basically you are making a lot of picture of the bridge in different time, but also from different parameters. If you don't keep the synchronization as important value as basically with different type of protocol, we provide the precision time protocol as well as the network time precision. Basically, in this case, the time lapse is about microseconds, even milliseconds. If you don't have this type of requirements, then basically you are not able to match all this information in processing, and you cannot have a really robust overview of your bridge. The third pillar is the precision, and for this, for sure, we have a diamond in this regard, because our sensor, our K-beam MEMSA capacitive accelerometers are the best in the market for this value. Among the different K performance parameters, I would like to highlight in this occasion the noise level that is almost zero, so it's 7 micro-G. Imagine that you have a different quantity of noise that you can capture in this big complex project as bridges. In this case, with our sensor, the noise level is kept very, very, very low. In this regard, for sure, we can provide a very high level of accuracy that is really important to extrapolate the modal parameters as natural frequency, mode shape, and all this information are related also with the damage detection. So it's really important to keep a really high precision and high performance, especially, I would say, and also in extreme environmental conditions as those one that are affected the bridge, because you know that there are in outdoor conditions with very different range of temperature among as summer, winter, and also day and night. Last, this is the integration. For this section, we defined, I think that it is the core of this presentation, because in Kistler we developed since a couple of months our unique solution in the world. Why? Because we are able to provide two different technologies, and also we are defining a new methodology to provide a bridge performance that is almost an overview between the structural response that is made by SHM, so different integration of, the integration of different sensors, and the weighing motion. The weighing motion is important because we are able to collect data from traffic and extrapolate information about the really important action. So as you explain now in the next slides, basically, this is the typical current layout that we can deploy on a bridge. We have on the left side the weighing motion that is able to monitor the traffic loading and give important insights about the gross weight vehicles, axle load, tire screening, speed, this axle distance between different cars, and give to us really good insights about the information of the traffic that for us is the main action that affect the bridge. In the other side on the right, you can see the structural monitoring system that is able to collect information about the structural response, how in continuously way, so 24 hours for 7 days by 7 days, because especially for critical bridge, we cannot miss a window specific in a day, and we need to correlate this information. For us, the methodology starts as from engineering point of view, especially for structural design problem, which with this definition. Basically, we have a comparison, a conflict between actions and resistance. For a structural designer, the most important thing is to keep into account the gravity force, the wind force, the seismic force. But at this point, traffic loads are always missed. In the other hand, you have the resistance that they are defined by the structural layout, so the shape, the dimension of the bridge, also the materials, the design load, and hopefully if the action are less than the resistance, the bridge can stand. So from a definition point of view, I mean, the problem I think that is really easy and really simple. But in the other hand, my question was why there is not a SHM system or a monitoring system deployed to resolve this problem? Because actually, since the last 50 years in a worldwide scale, the best practice for defining the action is basically there are some codes really obsolete and really old that with a probabilistic approach try to define the traffic curves and define the traffic load for each type of bridge and category in terms of roads. So unfortunately, they are not underestimating. Sorry, you can go a little bit in the previous slides. Yeah. So they are not defining our action. In the other end, to define the resistance, actually, since now there are visual inspection, they are already outlined by Kyle, and also the structural model, that they are missing, unfortunately, a lot of information. So with our system, we are able to measure both parameters because the action, as I told you, are recorded by the WIM with a live load spectra, and the resistance are outlined by the sensor located on the bridge. The final output is a comparison between the actions and the resistance that is named load rating. But to do this load rating, we are not taking into account assumption or hypothesis, but real measurement real data related with the real specification of the site in a real and continuous way. To prove this methodology, we have a couple of success stories. Basically, we can show the first enforcement for protection. This site is really famous in New York, is the Brooklyn Queen Expressway. Is one of our success stories, and basically with our weighing motion, the New York City DOT was able to reduce the number of overweight trucks less than 60%. So imagine that in this particular condition, in this critical and pivotal connection in a city like Manhattan, you cannot stop the traffic, but you need to limit. You need to put some limits, and you need to keep open the bridge. In this case, weighing motion was the best tool, also because it was the first example of automated citation system in US. For the second case, unfortunately, I cannot renown the name of this bridge because it's sensitive information, but I can say with a really proud self that is one of the biggest, or at least the biggest installation in the world of weighing motion lines. And in this case, the owner of the bridge, the biggest concern was that the main span was be demolished for some concern, some cracks in the piers, and the other bridge, the other span, has the aim to have the 50% more of the traffic on it. So it's a really particular problem. And for this application, there we define the more than 10 lines of weighing motion, digital one, and also we define the position of more than 200 SHM sensor among accelerometers, strain gauge, inclinometers to give a full overview of the project. All these data are sent to our cloud, and the analytics basically are able to define a live load rating for this specific, really critical condition. Yes. As you can see here, there is like a demo representation of basically our system, our software looks like. You can see that in the first mirror, we have a dashboard. We have a synoptic view on the bridge where all the sensors are located. We have green dots. For example, in this case, we are representing the location of the accelerometers. In the orange dot, we have environmental parameters recorded by, for example, the weather station. While in the right side of the slide, you can see all the channels they are recording. We have temperature, acceleration, inclinometers, and so on. And in the smallest one, there is a digital twin representation of this bridge that we are developing with ETH of Zurich. Yeah, I think that that's all. I hope that now we can trigger obviously some interest from the attendance, and that we are able to respond to your answer to your question and to your curiosity. Thanks for this opportunity.
One of the questions we got in the chat, maybe Giacomo, you could take this one. There's a question about Kistler sensors, for an SHM solution. Are all of the sensors provided by Kistler, or are some third parties? Can we integrate third-party sensors with our SHM solution? You want to touch more on that, Giacomo?
Certainly, I think that is an interesting question. Since we are expert in dynamic measurements, so we can provide different type of sensor for these purposes. Obviously, the main core is made by the K-beam MEMSA capacitive accelerometers, but we have also different type of accelerometers like the HEPI, and also in our portfolio we have different sensor for other purposes, like for strain gauge dynamic, for acoustic emission. I would say that since the topic of SHM, as I show you, there are different and a lot of parameters. For sure, we can integrate other third-party sensors correlated with the specific needs of the customer and the specific needs of the bridge. Because in a complex project like those one, there are different peculiarities and criticalities. But since now we are integrating tiltimeters, strain gauge, we have also fiber optics and weather station. Because the biggest pro that we can, with our data logger, we can integrate all this type of sensor without any problem.
No, thank you, Giacomo. Another question came in, and I believe everyone should be unmuted or able to unmute, but if there's any issue with that, feel free to drop a Q&A in the chat. Another question is, and Giacomo, maybe you could touch on this as well. How is the reliability index computed? If you look at how we address the live loads and the structural response, can you touch on reliability index along those lines as well?
Yeah, I mean, I don't want to be boring with some complicated formulation, but basically with our partners, we are developing a sort of tool for the analytics that is perfectly following the Hashto codes, so where load rating is defined, and is a sort of ratio between action and resistance. Among the different and several parameters that are located in this formula, for sure we have live load, that is some value that we can directly measure. We have gross weight vehicle, we have the Girder distribution factor, we have also dynamic amplification factor, and I would like to emphasize a little bit more on the latest one, because sometimes in the live load load rating calculation, this parameter is missed. Luckily, with our accelerometers, we are able to give the correct importance to this value and give a more robust assumption, a more robust calculation. And yes, actually, I mean, the most important thing is that we are not putting some value from some statistical recognition, statistical evaluation, but we are really measuring it on both sides. So our reliability index is site-specific, is site-based, is not hypothesized.
Thank you, Giacomo. Hopefully that answered the question. If there's anything else from the audience, you should be able to unmute now. If there's any other questions, feel free to chime in. Angelica, can you take us to the wrap up? Can you hear us okay?
Yeah, I can hear you just fine. Can you
Okay.
hear me?
Yep, we can.
I think there was one more question from Pete asking if the weather sensors are proprietary to Kistler or if that's a third party as well.
Is a third party.
Yes, correct.
We have sensor for wind, for temperature, and for humidity. Yes, but they are third party.
There's also another question about electromagnetic immunity. Giacomo, is that something you can talk to as well, or?
Could you say it again? I didn't get, sorry.
Question about electromagnetic immunity. Are there any issues or interference with electromagnetics, or is that something that we've dealt with in the past?
At this point, I would say that we didn't have any issues. I think that is mostly related how you connect the cables and which type of logistic you provide for the system. At this point, actually, our customer are always satisfied by the quality of the transmission of our data without any issue.
Well, thank you. We're going to start wrapping this up. Feel free to capture our QR codes on the screen, contact us directly with any further questions that you may have, enter any topics that you would like to see more webinars on in the future. We should be having another webinar before the end of the year. And we appreciate your time. Thank you to our speakers for diving in with us today. And we want to thank you all for joining us in this topic in this webinar today.
Thank you, everyone.
Thank you, everyone.
Have a great day.